One point moves around a circle of radius 1. For any angle theta, where exactly is that point? And if we record its horizontal and vertical positions, what shapes will those two coordinates draw? Start with the horizontal coordinate. The radius has length 1, and its angle from the positive x-axis is theta. In this right triangle, cosine is adjacent over hypotenuse. The hypotenuse is 1, so the adjacent length is cosine theta. Now read the vertical coordinate from the same triangle. Sine is opposite over hypotenuse. Again, the hypotenuse is 1, so the opposite length is sine theta. One point has supplied both coordinates. That gives the unit circle coordinate formula. P of theta equals cosine theta sine theta. But the right triangle is about to collapse. At 90 degrees, its horizontal leg has length 0. The coordinate definition still works. The point is 0 units across and 1 unit up. So cosine is 0 and sine is 1. Move into the second quadrant. The point is now left of the y-axis, so its horizontal coordinate is negative. But the point is still above the x-axis, so its vertical coordinate remains positive. Because x is cosine and y is sine, cosine is negative here while sine is positive. The 4 sine patterns are not a table to memorize. They are simply right, left, above, and below. Now use the circle to find an exact value. Where is P when theta is 150 degrees? 150 degrees is 30 degrees before 180, so the reference angle is 30 degrees. The familiar 30-degree triangle has horizontal length square root of 3 over 2 and vertical length 1/2. Reflection across the y-axis preserves both lengths. Only the horizontal direction changes. So x is negative square root of 3 over 2, while y is positive 1/2. Therefore, P at 150 degrees is negative square root of 3 over 2 1/2. The coordinate formula now reads both exact trigonometric values directly from the picture. Exact values are snapshots. Now let the point keep moving and record the horizontal coordinate against theta. At 0 degrees, x starts at 1. At 90 degrees, it reaches 0. At 180 degrees, it reaches negative 1. Continuing the same motion brings x back through 0 and then to 1. That continuous record is the cosine wave. Record the vertical coordinate in the same way. It starts at 0, rises to 1, returns to 0, and falls to negative 1. After the final rise back to 0, the vertical record is complete. That continuous record is the sine wave. The waves are not separate inventions. There are 2 readings of the same circular motion, width and height. Cosine begins where sine will arrive a quarter turn later. Their shape is the same. Their timing is shifted by 90 degrees. In radians, that quarter turn is pi over 2, and 1 complete turn is 2 pi. Add 2 pi to any angle. The point makes 1 full turn and lands at exactly the same place. Its horizontal coordinate is unchanged, so cosine of theta plus 2 pi equals cosine theta. Its vertical coordinate is also unchanged, so sine of theta plus 2 pi equals sine theta. The period is not an arbitrary property of the graphs. It is the angle required for the point to complete 1 turn. One more fact is hidden in the same picture. No matter where P moves, its distance from the origin remains 1. Horizontal and vertical coordinates are perpendicular legs, with the radius as hypotenuse. Pythagoras gives x squared plus y squared equals 1. Replace x with cosine theta and y with sine theta. The result is cosine squared theta plus sine squared theta equals 1. The identity is simply the equation of the unit circle. So one coordinate formula contains the whole story: exact values, sines, periodic motion, and both waves. The circle gives the coordinates draw the waves, and the radius keeps every point tied to the same identity. Try the same method at 210 degrees. Which signs change, and which exact lengths stay the same? Subscribe for more math made visible.